The decision tree has been constructed from training data. And it includes a node like this. Towards the leaf. It is towards the bottom of the tree. So a decision tree has been constructed up here. One of the bottommost subtrees looks like this. It has a left child that yields a prediction of C1. Why does it yield a prediction of C1? Because when you were building the tree, when the algorithm was building the tree, it selected V, and it found out that there was only one instance that was in the original training data that was placed in this subtree. And that one instance was a member of C1. Of the training data that percolated down this tree, 3 instances were associated with a 1 value of V that were all a member of C2. Okay, so we built the tree. Now, intuitively, let's say I started with 10,000 instances or 1,000 instances. I started with a very large number of instances in my training set. And I came down here and I built this subtree based on a total of 4 instances. Because these were all the instances that came down this one path of this decision tree during construction and came to this point. And I selected V in order to get these pure classifications that we were talking about using as a termination function earlier. Intuitively, does 4 instances carry a lot of statistical weight? Do we want to make decisions based on 4 instances where we may have started with many? Well, I started off by telling you about pessimistic biases and optimistic biases. And so it might be, if I have an optimistic bias, if I'm optimistic about the utility of information in the data, I might actually choose to keep that, okay? But if I'm pessimistic, I might choose and say, you know, this is too little data to make a decision like this on. And why can that be a problem? It can be a problem because it actually leads to a reduction in accuracy. Here I sketch out what would happen during test. That is, I've got a large number of items at test that are classified down this path to this node. 50% of these come down here. 50% have a value of -1 on V. 50% have a value of 1 on V. But in the post-classification analysis, everything that comes to this node, 25% of everything that comes here is a member of C1, and 75% of everything that comes here is a member of C2. Okay? But of the half items that come down here, so what should I do rationally? What I should do rationally if I want to maximize my prediction accuracy is if 75% of the items that actually come to this node are members of C2, I should just predict C2. I should choose the maximum most probable outcome. Because it's also the case, and this is important, that 75% of the items that come here at test are also members of C2. But for the 50% for the half of the items that come here, I'm always predicting C1, even though the majority are C2. And for the items that come here, I'm making a correct prediction. I'm correctly predicting C1, or C2 rather, for these, but not for these. And so if you were to compute the error rate based on these various conditions, and you can go through and confirm them, 50% that come down here, 50% that come down here are going to be, the 50% that come down here are going to be majority C2, but I'm always going to be predicting C1. And so 75% of the time I'm going to be wrong. 50% of the time, for 50% of the items that come down here, I will be wrong 75% of the time. For the 50% of the items that come down here, only for 25% of the items, those that are members of C1, will be incorrectly predicted. And so you compute that, and the error rate, the number of errors, the percentage of errors is going to be 0.5 for things that are classified down to this level, based on the conditions that I've outlined here. But if I were to simply have built a decision tree that terminated early, where 3 things were members of C2 and 1 thing was member of C1, and I simply predicted C2 here, the error rate would only be, the accuracy rate would be 75%, the error rate would be 25%. And so that's why we want to pay attention to overfitting the data, because it actually leads to a reduction of accuracy in some cases. So study this. Good chance you'll see something like this in the future when we talk about decision trees. And so what most decision tree algorithms will do is they will have different mechanisms for mitigating overfitting and the problem of overfitting. And they will do some kind of statistical test. Anyone have statistics? You guys have statistics yet? Studied chi-squared, maybe some other statistical tests, something like that. We're typically, during this decomposition process, going to decide and going to ask at each point, am I statistically justified in advancing the growth of the decision tree at this point? Is there a sufficient statistical basis for continuing? And one of my favorite data sets is political voting records of people in Congress. It's a great data set, all right? I'm not going to talk about politics, but turns out an extremely simple decision tree will separate votes from the 2 political parties. And this was true even in the 1980s, okay? Very simple decision trees, because you won't, maybe, you know, this is still an issue, immigration. Star Wars, anyone know what Star Wars might represent? You want to give it a go?
Yeah, during the Cold War, Congress and Ronald Reagan wanted to build a defense from
missile defense system, yeah.
Basically have it in space.
That's right.
Orbiting Earth.
That's right. So this was a big issue that Congress voted on. So this is old data. I don't want to get us involved in current, but this is old data. But if you want to go dig up voting records and just go to Congressional Quarterly, you can get voting records for Congress and run a decision tree algorithm on them. I think it's interesting to look at. And you can look in various kinds of detail. But in this case, party is the class, Republican or Democrat, and these other variables like immigration, Star Wars, these are the independent variables, the things, the items, the bills that Congress voted on. And as we're decomposing the decision tree, what we would typically do to determine whether it was worth decomposing is we would be at a node and we were considering whether to branch on immigration. Let's say immigration had the highest value according to our selection measure. If immigration had the highest value according to our selection measure, the thing we just looked at, that long thing with logs in it, information theoretic measure, then we would do an additional test. And that additional test would ask, okay, this seems to be the best according to the selection measure. Is it statistically valid to branch on this? And we would take a look at the actual distribution of the value along the values of immigration and political party We would also do, these would be the actual counts. These would be the predicted counts based on the assumption that these two attributes were independent. So under the assumption that immigration was statistically independent from party, these would be the projected counts. All right? And we compare the distribution. This is one way of doing it. We would compare the distribution under the assumption of independence with the actual distribution. And the chi-squared measure would say, are these sufficiently different to judge them to be dependent versus independent? And in this case, the chi-squared measure, at least at reasonable levels of confidence, would say, yeah, these are sufficiently distinct. Conclude that the relationship between party and immigration is meaningful, and go ahead and branch on immigration. Okay? So that's an example of a statistical test that could be used. There's actually lots of different variations on both the selection measures and the termination conditions. So the information theoretic measure was something we used for selection. The termination function, we started off by thinking it might just look for pure classes, but it also might do a statistical test here to see whether there was a statistical justification in doing the split. If there's not, then you just return the class note.